Yeah, next topic is retention index. Yeah, it tells how relative retention time of polar and non-polar solutes change as the polarity of the stationary phase changes. Okay, let's look at these two chromatograms. Okay, for different stationary phases are used for separating the same 10 compounds. Okay, but the figure A was obtained with a non-polar stationary phase, which is polydimethyl siloxane. In the meantime, the chromatogram B was obtained with a strongly polar polyethylene glycol. Okay, the thickness is the same. Yeah, 1 micron thick stationary phase in 0.32 millimeter diameter and 30-meter long open tubular column at 70 degrees C. Okay, and as you see, yeah, they both columns give the separation rather well, and the separation order is quite different. Okay, and here with this non-polar um, stationary phase, actually this is elution time. Okay, it's roughly uh, in the order of increasing boiling point. Okay, for example, the compound one, um, compound one, yeah, and compound two uh, are eluted first. Okay, compound one is acetone. Acetone is what? Is a polar molecule, and compound two is pentane. Pentane is quite a non-polar molecule, yeah? And it's a linear alkane, and it is very rapidly eluted. Okay, and compound three here, which one? Which is propanol. Which propanol is also um, a quite polar molecule. Okay, so N4 is methyl ethyl ketone. Right, ketone is kind of polar, but not as polar as propanol. And five is hexane. Hexane is completely non-polar. And six is butanol is polar molecule. Seven, 3-pentanone is also polar molecule, and 8-heptane is completely non-polar molecule, and 9-pentanol is polar molecule, and octane. Okay, um, so roughly, yeah, here are the boiling points. Okay, so the elution was done in order of increasing boiling points, but uh, this chromatogram, okay, with strongly polar stationary phase, yeah, the order is quite unexpected. Okay, the compound 2 was eluted first. 2 is pentane. Okay, uh, this one comes first. Why? Because uh, pentane is strictly non-polar molecule, and the size is small, so it doesn't retain, you know, in this strongly polar stationary phase. So it, 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 it is not interacted virtually. It is not interacted with the stationary phases. So it comes first. And five also. Five is hexane. Pentane and hexane, they are different only what? Hmm? The number of carbon, by one. Okay, and then eight is heptane. Yeah, they are all same. The alkane, and 10 is octane. Okay, and then one is acetone. Acetone is a polar molecule. Okay, so it retains longer in this polar stationary phase, but acetone is a small molecule, so it is retained in this polar um, stationary phase but a lot longer time. And 4, and then methylated ketone. Yeah? Acetone is also ketone, right? But methylated ketone is a larger ketone than acetone, so it retains in the polar stationary phase longer time. And then solvent, and then 7 is 3-pentanone, is also a polar one, yeah, polar molecule. And then 3, propanol is quite polar, yeah, much polar than acetone, okay, or methylated ketone. And 6 is what? Butanol, right? Butanol is also very polar, and it size is bigger than what? Pentanol, propanol. So it retains a longer time in the stationary phase. And then finally 9, the pentanol, okay? Yeah. That way. So when you use the polar stationary phase, polar solutes are retained long via hydrogen bonding or dipole interactions. Okay, so with, for example, propanol, butanol, or pentanol, and with the this polyethylene glycol stationary phase, there is a hydrogen bonding. Okay, but what about the acetone? Yeah, acetone and this stationary phase, there is no hydrogen bonding, but which one? Which interaction? Dipole interactions. Anyway, these interactions, you know, make the retention time longer. All right, but for strictly non-polar solutes, yeah, they don't have virtually they don't have interaction with the polar stationary phase, so they come very early. All right, but how do we uh, quant- quantitatively treat that retention time? Okay, here is the Kovacs retention index I. Okay, this retention index relates the retention time of a solute to retention time of linear alkenes. So in this Kovacs retention index, the reference is linear alkene like pentane, which has 5 carbon atoms, and hexane and 6 carbon atoms, and heptane 7 carbon atoms, and octane, yeah, and so like, okay, and the like. So for linear alkanes, I retention index is given by the 100 times number of carbon atoms. Okay, so for octane, Kovacs retention index value is 800. Yeah, because octane has this is a linear alkane, and it has 8 carbons. Okay, but what about the other compound? Yeah, and then this Kovacs retention index, the equation is rather complicated. Okay, let's take a look in detail. Okay? I equals 100 multiplied, okay, by parenthesis n. Here is the small n, large n. Small n is what? Number of carbon atoms in smaller alkane. Okay, now you compare, yeah, two different alkanes. Okay, and large n is uh, large alkane. So for octane and nonane here, yeah, n is small n is for octane, and small n is 8, and large n is nonane, n is 9. Okay, and here this part, pay attention to this part. Yeah, you measure adjusted retention time for unknown, yeah, which is tr prime. Okay, unknown. And then this log tr n is what? Adjusted retention time for small n. Okay, for octane and nonane. This one is for the octane. Okay, and divide by adjusted log of adjusted retention time large n. In this case for nonane, and minus logarithm of adjusted retention time for small n for octane in this case. Okay, yeah, this is the Kovacs retention index. Okay, yeah, here is an example. Here, if this one retention time for methane. Okay, just retention time is what? Yeah, you measure the retention time minus the retention time for unretained molecule, which is methane. Okay, and retention time for octane is 14.3 minutes, and for unknown, um, you measured 15.7 minutes, and for nonane 18.5 minutes. Okay, and then for this unknown, you can calculate this retention index I. Okay, let's calculate. uh, is 100 and times parenthesis 8, yeah, with small n, and parenthesis 9 minus 8 parenthesis, and then what? Yeah, this unknown is 15.7, but you subtract this retention time for methane, right? And then you get 15.2. Okay, and minus log this one small n, yeah, this octane, and you subtract zero point 0.5 minutes, so you get 13.8. And likewise you calculate the denominator, and for the no name you get 18 for the adjusted retention time, and this one for the octane, and then you get 836. This one, this value is that Kovacs retention index. Okay, so now you obtained this 836, this value, and this value is in between for 800 and 900. Okay, 800 is what? For octane, and 900 is for nonane. And then simply by looking at this number, and then you can you know immediately that, oh, this unknown compound, it will be retained come out between octane and nonane. Okay, the concept is like that. And this table tells retention indexes for several compounds on common stationary phase. Okay, yeah, this one is the stationary phases. All right, this one polymethyl siloxane is a very non-polar stationary phase, and benzene retention index is 657. Okay, and then now you know that immediately this is between 600 and 700. Okay, and then you know that, oh, benzene, you know, it will come out after the hexane and before heptane. Okay, like that. For the butanol, yeah, you'll know immediately that this one is also come out after uh, hexane and before heptane, but a little bit earlier than benzene, because this retention index is smaller than this benzene, like that. Okay, and then now you just take a look, and then let's take a look at this one, polyethylene glycol. Right, this is quite no, polar, strongly polar stationary phase. Okay, and benzene retention index is 956. Okay, and this one is polar molecule, so it retains longer. Okay, here 1142. Okay, so but with this non-polar stationary phase, benzene, this one butanol comes out first, before the benzene. But here, by changing the stationary phase to strongly polar stationary phase, this one butanol, the appears much later than benzene, like that. Okay, so this retention index tells you about rough, not roughly, rather, precisely when these compound will come out depending on these what stationary phase. Okay, so very useful. And next topic is temperature and pressure programming. Okay, usually when while you're running the gas chromatography, okay, and then you usually program the temperature. Okay, and also you sometimes you may program the pressure. Okay, but the pressure programming is not often done. Okay, but temperature programming is often done. Yeah, this is very usual practice. Okay, which part program the temperature, injection port, and also column, and sometimes you temperature program the detector part. Okay, a large fraction of all gas chromatography is run with temperature programming. This is quite usual practice in which the temperature of the column is raised during the separation to increase the analyte vapor pressure. Usually you program the temperature of column. Of column is in the oven, so you program the oven temperature. Okay, very precisely, right? Raising column temperature, no, causes decreases retention time. Okay, when you raise the column temperature and then uh, you know solute now moves very fast, yeah, receiving the thermal energy, so retention time decreases, and since it decreases, the peaks becomes sharper. Okay, so increased temperature is important, right? If you don't increase temperature, yeah, you maintain constant temperature, sometimes it will take more than an hour to elute all the compound. But with the temperature programming, the one run of chromatography will be quite short. Okay, so temperature programming is to increase the solute vapor pressure. Okay, so if you increase temperature, vapor pressure also increases, and decrease retention time of late eluting component. Okay, look at that. This guy, this 9, this alcohol, which one? 9 is pentanol. Uh, appears about 18 minutes later after injection. Sometimes it is too long. Okay, so if you increase the temperature, this one will appear very early. Okay, so that's very important. uh, at constant temperature, the more volatile compounds emerge close together. Okay, the less volatile compounds may not be eluted. Okay, that means that a constant temperature, if you don't program the temperature, highly volatile compounds emerge, you know, at the same time. So separation is not very good. But the less volatile compounds may not be eluted. Okay, so this is not volatile. So it may retain in the column for a long time. If increase, if you increase temperature from 50 to 250 degrees C at a rate of 8 degrees C per minute, okay, this is just an example. All compound elute. Okay, why you start at the low temperature? Because to separate, better to have a better separation of more volatile compound, and you increase up to 250 degrees C to elute less volatile compound. Okay, but do not raise temperature so high. Okay, that analytes and stationary phase decompose. Okay, too much high temperature may cause decomposition of analytes and stationary phase. Okay, and also pressure programming is done sometimes. Increasing inlet pressure causes increasing flow rate in a mobile phase. Okay, so now increase, that means you push hard. Okay, that means the your flow rate increases in mobile phase, and decreasing As a result, it causes decreasing retention time. Okay. In some cases, programmed pressure decreases retention time instead of using programmed temperature. Okay. Sometimes programming pressure is more desirable than programming temperature, but I don't see that case. It is useful for analytes that cannot tolerate high temperature. Yeah, okay. So temperature programming is a very efficient way to reduce the retention time, but as mentioned here, too much too high temperature may cause decomposition. In that case, programming pressure is a better way. At the end of a run, pressure can be dropped rapidly, okay, to initial pressure, to initial value, yeah, for the next run. Okay, next run must start at the low temperature. Therefore, time is not wasted in programmed pressure. Okay, so pressure drop rapidly is important. Yeah, if you slowly dropping pressure, that means longer time. Okay. However, time is sometimes wasted in prime temperature because the hot column to cool down before the next injection. Okay, and also the temperature prime the experiment. You also you have to drop the temperature to the initial value. Okay, after you increase the temperature here. Yeah. So, but um, changing temperature is not rapid. Okay, it cannot be done rapidly. So you need more time for temperature programmed experiment. Okay, so in a modern instrument, yeah, modern chromatographic instrument, so the when decrease the temperature to make the temperature decrease rapidly, and the the oven is opened. Okay, so the old heat may come out of the instrument rapidly. Okay, and here this chromatogram shows the programmed temperature chromatography of linear alkane at three different heating rates. Okay, here for the this programmed temperature. Okay, a 3 meter long polymethyl dimethyl polysiloxane column, yeah, etched in a silicon chip. Okay, here now only difference is that what the temperature raising rate. Okay, they all program the temperature experiment. Okay, when you increase the temperature 20 degrees C per minute, yeah, and then it may take longer time. Yeah, so in order to separate C15, you have to wait until, let me see, more than 300 seconds. Yeah, about 7 minutes. Okay, but if you program uh, the temperature rate is high, and then this separation can be done rapidly and with higher the rate, and then more rapidly, you see, you can separate all these hydrocarbons. Okay, let's stop here.